All right. Hello, everyone. My name is Alex Forensic. I am a postdoc at UC San Diego, and I do a lot of work in networking and optical switching, and I do a lot of work with FPGAs. So today I'm going to be talking a bit about building a AXI DMA interface for the Corundum open source NIC. So I'm going to start by going through a couple of slides here to give some background on the current setup in Corundum and the data path. And then we're going to take a look at taking the existing PCI Express DMA code and seeing if we can convert that to speak AXI instead of PCIe. So we'll see how it goes. All right, so Corundum is an open source NIC project that I've been working on for basically the last couple of years, and it's gone through a bit of an evolution. So let's see, as of, hang on, where's my mouse? Okay. As of, I think this was about September of last year, this is more or less what the data path on the NIC looked like. So what a NIC does is it takes data from host memory and it will transmit that over the network, or it will take data from the network in the form of packets and it will write it out into host memory. And that interface, at least in the initial version of Corundum, was done via PCI Express. So we've got the PCI Express interface here, and then that's connected up to several internal modules. So the completer modules are how the driver and the host software would communicate with the NIC to change settings or informative packets that need to be sent or whatever. And then there's a DMA module, and this is how the NIC issues memory read and write operations over PCI Express to fetch data for transmission or to write out received data from the network. Now, when I first started thinking about building Corundum, the idea was to do everything in a streaming interface. So instead of using AXI, just use AXI Stream. But the problem is there's all sorts of reordering that takes place on PCI Express between when you issue a read request and when the data actually comes back. That means you basically have to dump everything into a RAM for reassembly and reordering. So what I decided to do in the first iteration is to just use AXI. Xilinx had AXI DMA modules, so I figured, okay, if Xilinx uses it, it probably is going to work well enough for my purposes. So we put together, at least what I thought at the time would be a very extensible data path, where we just have a big AXI crossbar interconnect, and then we have the PCI Express DMA module, and then modules for each of the individual interfaces. So each SFP module or QSFP would have its own DMA engine. And then we would have a set of block RAMs on the other side of the crossbar interconnect to store packet data, that's being processed. So to transmit a packet, we would have the DMA module read the packet data from PCI Express, store it into one of these block RAMs, and then we would have one of the port DMA modules read it out and send it, or vice versa for receive. One of the nice things about AXI is the read interface and the write interface are totally separate. So that means a single crossbar interconnect is really two. You have one for all the reads and a separate one in parallel for all the writes. So if we dedicate one of these RAMs to, say, just handling transmit data for one port and another one for handling receive data, and we use dual port SRAM for each one of these, then you can get very good performance because the PCI Express DMA is only hitting one of the ports and these SFP modules are only hitting the other port. So that traffic doesn't interfere with each other. So we built this, and then we ran into all sorts of weird issues in terms of trying to get it to run at high speed. So I'm going to talk about those a little bit because it informs how the segmented interface that Corundum currently uses was developed. So these slides are actually ones that I put together for basically a status report meeting after I discovered some of these problems. So just for some context, for the experiments that we wanted to do, we wanted to have multiple 10 gig or 25 gig uplinks. So we started out with a single 10 gig port, but we wanted to have 3. So we need to run at least 30 gigabits per second or so. So we built this whole thing, we made it run at 10G, we could hit line rate, everything was good. And then we switched the Mac and Phi out for a 25G one and realized that we couldn't go any faster than about 10.4 gigabits per second or so. So yeah, so these slides are, as I said, as of September of last year. So at the time, the implementation had a few issues. Since this was kind of a rough design, there were some under and over estimations about various performance implications, and there were a bunch of stuff that I basically just punted on because I didn't have a good idea of, how to deal with it. And some of that I'm going to talk about in this presentation. So ignoring any back pressure on AXI, just looking at the PCI Express interface, we should be able to hit about 80% bandwidth or so. So if you're looking at a Gen 3 by 16 interface, that would be about 100 gigabits a second. But we should be able to hit closer to 90%, which would be about 113 gigabits per second. This is assuming 256 byte transfers over PCI Express with a overhead of 28 bytes per transfer for the header. But with our testing, considering all of the stuff going on in the AXI interconnect, we were only able to hit about 10.4 gigabits per second, which is terrible because with a 256-bit interface, we should be much closer to 50 or 60 gigabits per second. So the conclusion I came to is that we have to rewrite the DMA engine and the data path to improve the performance. So the next couple slides are going to talk about this in a little bit more detail. The first problem is back pressure in AXI. Now, one thing to keep in mind here over the next few slides is that when you transfer information over PCI Express is a packet switch protocol, and it uses things called TLPs, or transaction layer packets. And generally, the maximum size is 256 bytes. So on a 256-bit interface, it takes 8 clock cycles to move the payload of a TLP. Of 256 bytes. On a 512-bit interface, it's 4 cycles. So if we're paying any additional clock cycles for arbitration delays or anything else on a per packet basis, these are going to add up really fast because of the size of these TLPs and the number that you have to transfer for even moving a single Ethernet frame. For example, a 1500 byte Ethernet frame would be split into 6 of these TLPs. So if you're paying, 4 clock cycles per TLP, and it takes 8 clock cycles to transfer each TLP, then that's just going to totally destroy the throughput. So what we noticed is that there's a huge amount of arbitration latency through the AXI crossbar, something like 2 clock cycles per operation. And we actually had 2 levels of the crossbar interconnect. One to connect multiple interface modules, and then another one inside of each interface. And the arbitration delay of the second one was passed through the first one. So we ended up having something like 4 or more stall cycles per TLP that were being transferred through. And that just totally destroyed the throughput. So after some thinking, it wasn't clear if there was really any nice way to fix AXI. Right, we could go through and we could hammer on each one of these crossbars and maybe get some improvement, but it was unclear if that would really solve the problem. But after some more thinking, I realized that we could just drop AXI completely and simplify that interface and remove all of this arbitration delay and whatnot. And right, and the other thing is that we don't need the arbitration anyway, because there's really only one master module that we need, at least on the DMA side. So if I go back to the block diagram, what I was saying before about the way we were using these blockgrams is that one of the ports was basically dedicated to the PCI Express DMA module, and the other port was dedicated towards one of the port modules. So why do we need to share in this interconnect if we can just take these modules, move them onto the other side, and then we can have one port on each of these facing the PCI Express DMA module and one port facing the SFP modules. Now there's nothing to cause any back pressure. The memory itself doesn't. If we simplify this, and we don't have any other modules here that need to access this side, then that's going to significantly improve the performance. Now there is this other completer module here, but we ended up not using this. This would be used for maybe terminating DMA from, another device. But we never used that, and I don't think you even used it for, diagnostic purposes as a window onto the internal state. So if we get rid of that, then that reduces the logic resources, and it also means that we only need to have one module that's accessing all of the RAMs on the DMA side. So yeah, that was the first thing. The second problem is more inherent to the DMA engine itself. I figured that if we're going to be replacing the protocol, we might as well think about all of the implications and see if we can come up with something that's going to provide a much higher level of performance. That's going to be better geared towards operation with the DMA engine in the beginning. So when data comes out of the PCI Express interface, the data packed in those TLPs is D-word aligned with respect to host memory. But inside the NIC, the memory operations are all address aligned. So that means things need to be shifted into the correct alignment. So on a 512-bit interface, you might be getting 64 bytes on every clock cycle. But if you shift even by 1 byte, you need to add an additional cycle. So this is going to significantly affect the utilization. So it's like, let's say if the packet comes in like this, if we have one cycle which has 4 words being transferred and we need to shift by 1, well, then this last word gets pushed off the end and we have to move it in a separate cycle. So yeah, that's a problem. But we're always accessing an adjacent word in memory, right? When this gets pushed off the end, it doesn't end up in some random location in memory. It always ends up just in the location next door. So the original idea is, okay, what happens if we just double the memory interface width? Well, that doesn't solve the problem because some of the shifts you can accept, but eventually you're going to wrap around. But what if we provided 2 independent memory interfaces? So if we provide double the interface width in total, and then we put all of the even addresses on one and all the odd addresses on the other, then we can address all possible shifts within a single clock cycle, right? Because you can take these 4 and you can shift it however you want, and you can always make it fit into these 2. And if these are 2 separate memory interfaces, each one has its own address bus, and I can have this one look at one location down in memory, and everything works just fine. And then the third problem is the TLP header itself. So like I said before, the TLPs tend to be something like 256 bytes. All of the maximum payload size settings are powers of 2, which is cool. But the problem is that there's a header attached to each TLP, which is 12 or 16 bytes depending on the type of the packet. So that means on a 512-bit interface, well, let's see here. I have a little depiction of what it looks like when the TLP is sent down a link. So we have 8 data words here and 1 header word, right? So the issue is that as long as the headers are all appearing in the same lane, we end up with all these empty byte lanes at the end. And it ends up being 48 to 52 byte lanes depending on the TLP, which ends up being approximately 80% of the bandwidth. So that's a problem. We can still get pretty far without fixing that, but it would be nice to at least take that into consideration so we don't need to change the interface yet again. Xilinx provides a solution to improve what's coming out of the core, and that's called TLP straddling. And the idea is that you can have another TLP start in the same transfer cycle, in the same clock cycle as a previous TLP ends. So yeah, that means you can get 100% throughput here, but now we're dealing with, multiple independent operations per clock. And with some thinking, it seems like it might be possible if we limit the width to 128 bits per segment, that we might be able to sync these operations over the segmented interface. So I need to do some work on this. We haven't implemented this yet, but we did take the 128-bit max constraint in the current setup. Okay, so the proposed interface is we're going to do a something that's double the width. So if we have a 512-bit interface, do we make it 1024 bits? We're going to have a simple RAM interface, so no back pressure, no bursts, no arbitration. We're going to use simple dual port RAMs to connect the PCI Express AXI DMA, or rather the PCI Express DMA interface, to the DMA clients on the other side. And if we use simple dual port RAMs, then we can use LUT-RAM. If you need to use true dual port RAMs, then LUT-RAM doesn't work. So you're dealing with much more logic resource consumption for small RAMs. But the cool thing about doing this is we also get to use the RAMs as a clock domain crossing for free, basically. We haven't used this in Corundum, but it could be useful for other designs. Another advantage, or another feature, is we're going to use at least 2 segments, each at most 128 bits. So that means we should be able to sync operations even with straddling turned on, once we get around to actually implementing that. The nice thing about the split interface and client setup is it allows you to mix and match clients as well. So right now for Corundum we're using only AXI Stream, but it would be possible to have, a combination of AXI Stream, AXI Masters, AXI Slaves, various widths, various clocks, whatever, and everything will just hopefully work. So yeah, I also did some looking at, okay, if we're going to use this interface that's super wide, what does it look like in terms of resource consumption just to fill that interface in terms of the number of primitives that are required? So if you're using block RAMs or distributed RAM or BRAM, there's kind of a minimum size that it's going to take up in terms of logic resources. So there's no point in making a RAM smaller than that. For example, if you're using block RAMs, if you make a 32K RAM, it's going to take up 32 KB worth of block RAMs anyway. So yeah. Anyway, so this is what the block diagram looked like before. The idea is we're going to take all of that, delete it, and rearrange it like this. So we have a PCI Express DMA interface, then we have the DMA clients that are connected to the QSFP modules here, and then we have the dual port block RAMs in the middle that form the interface between the two. So the plan today is to take the PCI Express DMA interface here and to make an attempt to rewrite it to speak AXI instead of PCIe. Now we're probably not going to complete that, but we're at least going to start and see how far we can get. Oh, right, and then after we implemented this is what the performance figures looked like. So with AXI internally and 256-bit everything else, we got about 10.7 gigs. And then as soon as we moved to the new segmented interface, it popped up to full rate 25 gigs. And then when we moved to Gen 3 by 16, we popped up to about 50 gigabits a second, 40, 50 gigabits a second. And I'm not sure exactly what the issue was with this, because we moved to a different machine and we popped up to like 80 gigabits a second or something. So yeah, these were limited by, I think, something in the uncore, something on the CPU die limiting the throughput. So anyway, that definitely solved the problem. So let's take a look now at the existing PCI Express components and see about reworking them. So the current setup consists of, or at least on the host interface side, of 2 modules, the DMA interface PCI UltraScale read and PCIe UltraScale write. So this handles all the read operations and this handles all the write operations. The interfaces are relatively straightforward. We'll start with the write because it's a little bit simpler. Well, a little bit. This has, okay, so the other thing is that the read requests are actually passed through the write request module for merging. So the read requests from the read side come in here, and then this is the read request TLPs that actually go to the PCI Express hardcore and then out onto the bus. This module also keeps track of the transmit sequence numbers. I can talk about why we need to do that a little bit later. But yeah, so this accepts the sequence numbers from the hard IP core and passes the ones for the read operations through to the read side. And then there's some flow control stuff to make sure we're avoiding headline blocking. And then this is the control interface. This is where the requests to perform transfers come in from the user logic, and this is the status going back to the user logic, indicating that a particular operation has been completed. And then down here we have the segmented interface for actually writing this stuff out into the internal RAM. And then this configuration here is, well, I'm probably gonna have to rewrite this at some point, but the max payload size is the most important thing. That comes from the PCI Express hard IP core to determine how big of a TLP we can generate. And then the read interface is pretty similar. We have, this is the read data coming in from PCIe. These are the read requests going out that pass through the write code and then to PCIe. Sequence number, transmit flow control. This is the command input where we get the transfer requests from user logic, the RAM interface, where we can write the data out into the segmented interface, into those block RAMs. And then we have configuration and status. So this is extended tag and max read request size, and I'm probably gonna have to rewrite that at some point. Anyway, so what we're going to do is, and then I have a third module here. This one just instantiates both of those modules and has the necessary interconnections. Previously, this had some additional muxing and merging logic and whatnot. But since that was moved into the right side, then that's no longer necessary, and it's basically just those two modules directly. Okay, so I'm going to start, let's see. I'm going to start just on the right side, and we're going to make a copy of this file. Oops, right. Okay. I'm going to make this DMA interface AXI right. Okay. And I'll just make copies of all of them. Okay. So let's take a look at this. I'm going to go through and I'm going to remove everything in relation to PCI Express or rename it, as the case may be. So let's see. The PCI Express stuff, well, that's no longer going to be AXI stream. That's going to be just straight up AXI. And we can also get rid of the sequence number. We need the segment count. Well, let's see here. I should copy these from an AXI module. I'll pull that up in a minute. So I don't need this because I'm going to have an AXI address field. Tag width. I gotta double check on what that is. Op table, TX limit. Okay, TX limit, I think, well, I'll leave those alone for now. TX flow control enable. We don't need to worry about that here. Okay, so AXI input and output. These are going to be replaced by the AXI connection. Transmit sequence number, we don't need that. Transmit flow control, don't need that. There's the descriptor, the write descriptor, input and output, and the RAM interface, and then the configuration. I think all of this can go away except for enable. Okay, so let me take a look at my AXI code here. And let me pull, it's the standard AXI Master Interface. So this is, okay, let's see here. AXI DMA, this one has, here's the AXI Master Interface here. So we'll go ahead and make a copy of that. So that's going to replace this. Okay, so this guy, is there anything that I should get rid of here? I think this is all pretty standard. All right. So now I also need the corresponding parameters. Go ahead and take all of these AXI connections from here. And that will replace all of the PCI Express AXI stream stuff. Okay, max burst length. I'll go ahead and set that to max. AXI ID width, strobe width, address width, data width. Okay, that seems pretty reasonable. Okay, so PCIe data width, that is all going to get replaced. Well, I'll just start with the parameters for now. So this is going to be AXI data width. Okay, and then I'm also going to get rid of the whole 128 thing. Hang on a second. Yes, a seg count, that's just going to be 2. Because AXI doesn't support any of the straddling stuff. Okay, so we got data width. Okay, that looks pretty good. RAM address width. Okay, that looks good. All right, and I'm just going to set these to table size. I'm going to set this to AXI ID width. There we go. All right. In fact, well, I'm not sure about that one. Okay. Let's see. So this is not going to be the PCIe address width. This is all going to be AXI. So I'm going to replace all of those for AXI address width. Okay. We get the AXI address width. This is also AXI address. Oops, that should still be desk, but this is going to be AXI. Okay. Cool. So we're going to take this, and I'm basically going to comment out the whole module, and we're going to get the test bench set up for this so I can actually run it. Let me make sure I have all the necessary interfaces here. So I got the RAM interface, enable AXI read and write descriptors here. Oh, I should rename this. This is going to be AXI. And this is fine here. So this is going to be, okay, cool. Now I'm going to go over into my test bench directory. I'll run my test bench generation script. Let's see, DMA IF AXI write. Oh, I don't need dash I. That was an old version. Okay, I'll do that. Perfect. Okay, so we go down here. I have now, here's the test bench. And let's see if I can get this working for just a real simple test case. I'm going to go through, I'm going to start with a 64-bit interface here, AXI data width. I'm going to set that to 64. Oops, 64. Okay. We'll do the same thing here. Did I do that correctly, or did I replace some stuff that I shouldn't have? Yes, I replaced some stuff I shouldn't have. All right, I wanted to replace this one. Okay, so that's that. And then I need to do the same thing here. This gets an underscore 64, and this is 64. All right, cool. So let's see. To make this work, I need a couple of different modules to include in the Python side here. Let's see. Mainly I need, well, let's see. So DMA RAM, I will need that. Access EP, I will need that. I don't need any PCIe stuff, but I do need AXI. I do have AXI.py here. Okay, there we go. Let me see if I can run that. Let's see, didn't like something. Oh, didn't like my clog2s. Did I do that in the other ones? I'll copy the same thing. There we go. Oh, and I need to cast some of these to integers, don't I? Okay. Oh, I need to rename these files. Okay. Right, rename that. That'll be _64. The _64 as well. All right. So I'll start with the narrow 64-bit interface. Oops. Okay. There we go. Okay, so that, no errors yet. Okay. So let's see here. First thing that I need to do, I need to start bringing back is the code for accepting the new requests. So let's see here. Where would that be? That would be over here. So I call this TLP segmentation. In this case, I don't need to segment into TLPs, but I do need to segment into AXI operations. Okay, so bring the state machine back in, idle state, wait for incoming descriptor. Okay. Okay, so when this happens, what we need to do is store all of the information from that descriptor. So let's see, this is not PCIe address anymore. I'm going to go ahead and replace all of those with AXI. This will take a moment. Okay. So let's see. All right, so what this is going to do is mark that we're ready for a descriptor if there is space available in the internal table that we use to keep track of the in-flight operations. We're going to go ahead and we're going to take those parameters from the descriptor in, and then what we need to do is determine how big of a packet that we need to make. So this is where we need to start looking at various rules. So there is a max payload size to worry about. In fact, in this case, it's not a max payload size, it's the max burst size. And we also need to look for crossings of 4K boundaries. So we need to do that for both PCI Express and AXI. So this code is somewhat simpler. We don't have to throw everything out here. And then what we're going to do is actually start the operation. So the code in here is split up into a couple of different state machines. This first one accepts a new request, a new transfer request. And this one issues all of the necessary reads over the internal segmented interface. And then the second state machine accepts those, accepts the data from those reads, and or let's see here. Wait for read command. Oh, actually, I rewrote this a while ago. Okay, so this first state machine, it segments the requests into smaller pieces that satisfy these rules. The second piece then issues the reads against the internal segmented interface. Once those reads complete, then this third state machine takes over and actually generates the right request information, or the right requests over PCI Express. And then down at the bottom, we have all of the stateful logic, and we have some output registers as well. So this is just for the RQ interface for issuing the write requests. Okay, so let's go back up to the top here and bring in some more of these parameters that we need here. Okay, so leave those aside for now. This one, access PCIe data width. This one, actually I'm going to go replace all of these for just AXI data width. Okay, and RAM offset width, we got that word length, cycle count, sequence number. Okay, we have nothing, we're not doing anything with sequence numbers now, so that goes away. I think. I'll just leave that commented out for now. Mask FIFO. Okay, yeah, we need that. Tag width. Yeah, I think we need that too. Okay. All right, I'll deal with these assertions later. So these are parameters for all of the states. No, these are for PCI TLPs. So that can go away and that can go away because we're not using TLPs anymore. So these are all of the states for the 3 state machines. And data path, let's see, we'll need that. Let's see, we'll need all of these as well, except for maybe TLP count. We're not doing TLPs anymore. We're doing AXI read requests. Oh, actually, I don't need all of this, right? This is the write interface, so I only need the write signals here, which is the AW channel, the W channel, and the B channel. So let's see. Those all go away, and I can remove those from the other interfaces as well. Actually, before I do that, I'm going to copy this one. Let's see. I'm going to copy that one so I can just go ahead and stick it in the read code here, where I need the read interface, right? And then the combined module where I need the complete interface. There we go. Okay, so let me go ahead really quick and fix the test bench. Let's see here. Let's save these. And the test bench here, let's see, write 64. So I don't need any of the read interface stuff. So all of this goes away to there. And again, let's see, goes away up to there. Okay. And same thing here. And I think that's it from here. Okay, and then I need to do something similar here. All of the read interfaces go away. Let's see. R valid through A ready and AR ID through R ready. And then again, same thing. That goes away. Oops, that one as well. And then down here, same thing. Okay. And down here, same thing up through B ready. There we go. All that goes away. All right. Let's see. If I run the test bench again, it's probably going to complain about something. Right. Okay, so this is the PCI keep width. Okay, this one can be replaced with the strobe width. AXI STRB width. Okay, I think that's right. Oh boy. All right, let's see here. I need to bring in some more registers as well. So let's see. Let's see, I need the registers for interfacing with both the descriptors coming in and the status records going back out. And then I also need the operation table stuff. So the operation table is basically internal state that's used to keep track of in-flight operations. So whenever an operation is started, it's marked inside of the operation table. I'm going to come out to a couple of these other lines here real quick. TLP CMD tag. Comment that out for now. And then what was the other one? Max payload size. All right, I need to, I think that's going to be replaced by a constant. Okay. Force to in-out. All right, I probably just haven't specified something yet. Okay. All right, so let's see. In this case, next step here is to set up some more stuff in the test bench so we can actually issue some commands to the DMA engine. So I'm going to go and take a look at 2 existing test benches here. One of them being a PCI Express write DMA test bench. I'll take this one. And we need, let's see here. We need connections for the AXI stream interfaces for the descriptors. That's going to go, let's see, right over here. Okay, and this is not PCI Express. This is AXI address. All right, and let's see. Skip all the PCI Express stuff. I will need to pull in an AXI RAM module. I'll go ahead and copy all of that for now. And comment it all out immediately, basically. So I don't need the enumeration, but I am going to do just a single read, well, actually in this case, just a single write. Okay, so per tag, that's fine. Max payload size, I'm not using that. Okay, so enumeration, we don't need to enumerate anything. Okay, and this is just going to be a DMA write. We'll do the same thing. This is not PCI Express address. This is going to be the AXI address. AXI address, okay. So I'm going to try to write this to address 0, basically. And we'll see how that works. Okay, so DMA RAM, let's see. I think originally that was created from the PCI Express root port. What we're going to do in this case is pull up an AXI RAM model that we could use for the DMA engine. So let's see. I'm going to take from this write module here. Okay, so there we go. Here is an AXI RAM model. So I'll take that guy and we'll use that here. Okay, so this should have all the same connections. I'll go ahead and replace DMA RAM with AXI RAM. All right, so I think this has everything that I need. Okay, let me do a quick test. See if this runs. Create port got an unexpected keyword. Oh, I might have an old version of the AXI code here. User clock is not defined. Well, I'm not using PCI anymore, so I don't have a user clock. It's just clock. And I also don't have user reset. It's just reset. Okay. Membase is not defined. All right, I think that one is just going to go away. Where was that? Membase. Okay, that's right here. So that goes away. Okay. Well, that makes sense because the operation timed out. So I will go ahead and pull up the waveform. Okay, there we go. And we'll see really quick what we got here in terms of the operation. Okay, so enable goes high, and we go ahead and here is the write descriptor. So valid goes high, tag is 1, ready is high. Well, if write desk ready, oh, the reg is still low. Okay, the output signal is high Z because I haven't assigned it yet. Okay, but there we go. We can see length 4. Let's see, AXI address 0, RAM address 0. So that looks correct so far. Oh, I need one more RAM, don't I? Oh, actually, that's a good point. This should not be AXI RAM, should it? This should be, this should all be DMA RAM. Okay. See here. Oh, and then mem data. Yeah, that's right. Okay. Okay. Let's see. Where was that? I need to look at the DMA interface module here, and I need to pull out the DMA RAM. Here we go. PCIe DMA RAM. Well, in this case, it's not PCIe, but this is the same segmented memory that we're going to be using on the other side. Okay, so we got that, and we got the RAM. All right, so what we're trying to do very simply is read from this guy and write to this guy. Very simple. So what we're going to do is we're going to preload the DMA RAM with what we want to write. So we write that into the DMA RAM, and then we issue the operation, right? Let's see. Okay, that's what we issue the operation. We wait for it to complete, and then we go and check to see if that did in fact get updated in the correct location in the AXI RAM. So I'll circle back to this a little bit later once the test bench is actually showing that things are working. Okay. Oh, oops. I forgot to change the clocks again. Okay, so this should just be clock. Okay, there we go. That's better. All right. So this is now showing we have, let's see, RAM read command ready. So we're seeing both segments are indicating that they're ready. Okay, that looks good. Now I need to go back to the code here, and we'll see if we can get this DMA module to do something useful. Okay, so I'm going to ignore these rules for the time being. I'm just going to assume that the packet meets all of the required rules. And then I'll go implement those a little bit later. Okay, so let's see, TLP count next. So op count is operation count. I'm issuing a single operation here. Well, so op count keeps track of, where does that come from? That's the operation count, the number of bytes that are going to be transferred in that operation. So TLP count, although I guess I should rename that because we're not using TLPs, keeps track of how many bytes are going to be in the current transfer. So I'm going to take a look at this existing DMA module, and we're going to see what I did with that. Because this code actually does something very similar. In fact, I can probably copy some of this code from here. Yeah. Okay. So in this case, I used transfer word count. Because I have both a word count and a cycle count that I keep track of for some of this stuff, because it's just easier to compute both the word count and the cycle count ahead of time. So the word count is like the number of bytes you're transferring. And the cycle count is the number of transfer cycles, the number of clock cycles. And computing those is slightly non-trivial due to alignment issues. With PCI Express, it's not too bad, but with AXI, and if you're starting, all the way, if you have like an 8-byte wide interface, and you're transferring 1 byte on the first cycle, then you have to make sure you have the correct number of transfer cycles. It's not quite as simple as just bit shifting. You also have to add some stuff. Okay. So let's see. We have the TLP count. I'm just going to assume this is correct for now. Okay, and I'm going to change that to TR word count to match. So TLP count goes to TR word count. Hopefully I don't need to change this again. Okay. Well, I have another TR count reg. Where do I use that one? I guess I use that probably over here. Okay. Anyway, so this one goes ahead and this one, let's see. This one prints out oh, this is not a PCI DMA. This is an AXI DMA. Start right. Okay. So that one will print out some debugging information, so we can see what's going on from the standpoint of the Verilog, and then it will go to this start state, which starts all of the internal operations. So let's see. This computes the request size, and then this one is going to compute size of the subsequent operations. So let's see. In this case, we're not computing the TLP length. We're computing the transfer length for each individual transfer. So what all of this stuff does here is make sure that all of the necessary control lines are ready. So in this case, we want to make sure we're not overwriting an existing request has already been placed on the control lines out to the RAM. Okay, so in this case, we're going to pull all of this information from these internal registers and place them on the actual RAM read command outputs. And then let's see, data width is greater than 256. Let's see, this one was related to, okay, we actually, well, I think I need to do something about this. But this is related to the PCI Express header. In fact, I might be able to remove that. Okay. So what this code does is it computes a bunch of parameters in relation to the operation that needs to take place. So this computes really the subsequent AXI address, the subsequent RAM address for the next transfer, the number of bytes that still need to be transferred, and so on and so forth. Another PCI Express address that needs to be changed for AXI. Okay. All right, let's see here. So what else do we need to bring in here? I need to bring all this back in, I think. These are the commands going out to the RAM, right? Because this setup here is issuing all of the read operations. And I also need all of the fields in the operation table that keep track of the in-flight operations. Some of the stuff I'll rename a little bit later. Okay, let's see, what else do I need? See, I need to pull in a lot of the definitions of this stuff here. Okay, so I don't need anything in relation to sequence number. That goes away. So I can make these assignments. I can make those assignments. Okay. Let's see. So RQ, I have to put that together for AXI. RAM read command. Okay, I need that. So have credit, that stuff I don't need. Active TX count, inactive TX. I don't think I need to keep track of the number of in-flight transmit operations. That's necessary for PCI Express though. Let's see, mask FIFO, I need that. Read command, I need that. TLP command tag. Yeah, I'm just going to bring all this back in and then I'll delete what I end up not needing. Okay. Now I also need all of the stateful logic down here. Without this, it's not going to do much. Okay, so we have the state machine, the state variables, have all of these internal registers. Okay, let's see, write desk ready, I need that. Write desk status, oops. Okay, RAM connections, max payload size, I don't need that. Have credit, I don't need that. Active TX count, if I need it, I'll bring that back. Okay, then all of the operation table management, that goes away, or I need that rather. All of the, okay, sequence number, I don't need that. And then I have all of this stuff to get reset properly. Okay, all right. That's looking pretty good. Okay, so output data path here. This is for the PCIe TLPs. I'll revisit that in a little bit for actually initiating the AXI operation. So the first thing we need to do is perform the read against the internal memory. Doesn't like something. Okay, let's see, 513 syntax error. Whoops. Not sure what the problem is here. Maybe I just need another end. There we go. Okay. RQT ready reg. Where is that used? That's way down. Okay. Oh, yeah, I think I have a couple extra things that I don't need. RQT ready. Yeah, okay. That goes away. And TX count and TX AV. All right, so those guys go away as well. All right. Let's take a look at, okay, so this actually did something now. We can see the right descriptor source that sends all those parameters, and then we get AXI DMA start write. So it actually ran that first bit of code up here, indicating that yes, we're going to start this write operation. The source address on AXI is 0, the destination on the RAM side is 0, length is 4, and the tag is 1. So the tag will be returned along with the status information when the operation completes. All right, so let's take a look at we got here. A lot more signals, a lot of stuff that I have not yet initialized that I need to do. Okay. Okay, so let's see. The first thing that happens here is that we're going to pop over to the start state. And let's see. This is going to be looking at the RAM stuff here. Okay, so RAM RD CMD cell. Why is that coming up as all X's? Oh, because that's assigned down here. Okay, cool. So I'll go ahead and start bringing this stuff back in. Read CMD ready. I got all that. And then all this and the mask FIFO. Okay, so this is issuing all of the internal read operations. And I think this one is basically going to stay pretty much as is, because once we've segmented it out into a particular operation, then we're basically going to issue the operation exactly the same way as for PCI Express. So I'll run that, and we'll see what that looks like. Okay. That looks a little bit better. Okay, so what happened here? We should have CMD ready, or CMD valid. Okay, so it didn't issue any commands. All right, let's see. What did I miss for that? Okay, so what I need to do in this case is actually generate the necessary command for this second part. So this one generates the RAM command here. Okay, so I think that looks pretty good. Cycle count next. That's not quite right, but I will take a look at that in a little bit here. Okay, there we go. That did something now. So we have RAM CMD ready, goes high and then back to low. Oh, that's the read CMD. Okay, so the other thing I need to look at here is the RAM. Let's see. Read CMD. Okay. RAM CMD ready, RAM RD CMD valid. Okay, so I still have not issued one. That's fine. So this, we're making some progress here because this is now moving on to this next block of code here. RAM CMD ready is going high for one cycle. So RAM CMD ready, that's controlled here. So RAM CMD ready is set high here, and this moves into state read. All right. That's some progress. So these state machines communicate using this RAM read command set of signals. Actually, where are these set? Here they are. So this contains the AXI address, the RAM select line, the RAM address, and the operation length, as well as the cycle count and some other stuff that's kind of computed ahead of time. So some of this is things that I've had to do for timing optimization reasons. When you're running at 250 megahertz, you know, FPGAs are fast, but they're not that fast. So some of the stuff you have to do in an earlier clock cycle if possible. So that's what we had to do here. Okay, so what we have in this case is the RAM CMD, or the read CMD AXI address. Okay, so that's 0, that's right. CMD address next. The next one is 4, because the next read would, the length is 4, so the next read would start right after the previous one. Cycle count, I think that's right. I think it will do cycle count 0 if there's only one cycle. Let's see, CMD last cycle, that will be set if it's the last cycle. Okay, that looks right. CMD len is 4. Yeah, okay, so all of this seems to be correct. And this one is setting CMD ready to high. All right, so let's see now, what is going on the other end here? Let's see, so we're looking at RAM CMD address here, RAM CMD cell. Let's see, so this should be setting this high. Let's see, so RAM wrap next, I think that is not set. Should not be wrapping, yep, it's not wrapping. Okay, so wrapping is what happens if we're, if we've pushed all the way off to one end of the double width interface and we have to write, you know, 2 incremented addresses back at the start. So let's see here. That should be setting the RAM masks. So the RAM masks are which RAMs we're actually going to be touching. So yeah, RAM mask is X's. That's not correct. Why is that happening? So I think these are only used locally. So this is coming from start offset next and end offset next. Start offset is 0, okay, end offset. End offset is 3. Why is this coming back as X's? Let's see, this is read RAM mask 0. Oh, okay, actually that's a different thing. Read RAM. Okay, no, these are right. That is actually generating this here. Okay, so this is correct because for address 0, we're just going to be accessing the first segment. So there's two bits here. Bit 0 is 1. So that's correct. Okay. So that sets read RAM mask reg. Yeah, that should be right. Okay, cool. Okay, so now the question is, why are we not actually starting this operation correctly? So RAM mask reg, where is that one being set? Oh, that one might actually be set down here. Yeah, that one is set. That one is set there. So that's not a problem. All right, so why is this not issuing the operation? RAM read CMD valid, RAM read CMD ready, read RAM mask, and mask FIFO full. All right. Oh, did something not get pushed into the mask FIFO? That was another optimization I have to do, is computing what the mask value is early. Otherwise, you have all sorts of timing issues. Oh, and not RAM mask FIFO full. Okay, so the way this works is we compute the mask as to which RAMs we're looking at in the read side when we're initiating the read operations, and then that gets passed through a FIFO basically to the side where we're interpreting the read data and generating the AXI write requests. So that looks fine. So mask FIFO full should be low, I think. Mask FIFO, well, okay. There's at least part of the problem. Okay, where is that coming from? Let's see, so max FIFO, or mask FIFO full is coming from where? Okay, here we go. This is looking at the mask FIFO read and write pointers. Okay, so maybe those were not reset correctly. So those should have been set to 0 there. Mask FIFO read and write pointers. Okay. Oh, maybe the problem is that this pointer is getting screwed up here. Okay, so because this one reads from it. So there is the reg set to mask FIFO read pointer reg. All right, so I got to bring in this last state machine so we can actually issue these operations. Okay, so I got that, and let me go ahead. Let's see, I'll pull in. Well, it's not TLP state anymore, but I'll keep that for now. Got the status, read response. We got these fields as well. All right. Operation table, Zynq active TX. I don't know if I need that or not. And then I think I need something here so it will actually run something. If I have nothing here, then it's just going to ignore the block in the simulation. Oh, didn't like sequence number enable 989. Okay. All right, I'll leave this out for now. I'll come back to that later. Okay, so we actually now see commands at the DMA RAM. So it issued 2 reads. Couldn't have issued 2 reads, but it issued 2 reads. Okay, making progress. Mask FIFO write enable. So it wrote 3 things to the mask FIFO. Well, that's not correct. But it did actually issue the read. So here we go. We can see the read response data. It actually read it out. 11223344. That was the data that we want to actually DMA over the other interface. So that's a start. We issued that. We got the read response valid indication coming back. And the reason it stopped is because there's a couple of pipeline delay cycles, and at this point I think the ready line in the other direction is probably low. Let's see, or maybe not. Read CMD ready. Yeah. So that one's not accepting any more reads until that gets flushed out. All right, fair enough. But that did perform the read. So the next question is why this is still high. I think it's because I haven't finished that first state machine yet. Okay, so let's see here. So this has to record a bunch of stuff in the operation table. And then this computes the length of the next operation. So I'm just going to skip this for the moment and just do that. And let's see, so if operation table start last, this should go ahead and get out of this state and go back to idle. Okay, that looks better. Now issued a single operation. There we go. One operation this time. There's the data that came back. All right, so this is starting to show some signs of life here. So at this point, we've performed the read, I'm going to go back and clean up all these rules afterwards to get all this set up, but this is at least going to be a start. Okay, so I can get rid of this because the byte enables here are only used for PCI Express, or at least the way the first and last byte enables are done here. It's only done like that for PCI Express. Now in this case, I need to issue not PCI Express TLPs, but an AXI write operation. So let's see. How am I going to do that? I need to go ahead and add some infrastructure that's required for interfacing. So I'm going to take a look at my existing. This is just an AXI stream DMA code that I wrote a while ago. And I guess I originally used this in Corundum, but I'm not using it right at the moment. So I can go ahead and pull a lot of the data path logic from this, because we're basically doing the same thing. Okay, so this is for the W channel. I guess I don't have an equivalent one for the AW channel. So all this for RQ can go away. Okay. So that is one piece, and then I need internal data path. I need that. And then I also need connections for the address channel. So that goes here. That goes away there. All right, so this is now, let's see. So this is, where's RQ connections? Here's RQ. Okay. So this is now for the AW channel for AXI. So we need the ID, and in this case, I'm just going to set the ID to all zeros. For issuing writes, I guess I can probably change this up a little bit later. That doesn't make too much difference. Burst size, we'll transfer that. These are all just default values. We're only going to issue incrementing bursts, for example. Nothing locked, nothing strange in terms of protected, unprotected cycle. And AW cache is the cache settings. That basically means, well, actually I can't remember what those bits are set to, but those are the standard configurations for a an AXI DMA. Okay, so now I also need the registers that were associated with that. So this is the AW and B channel. Okay, where should I put that? I'll put that up here. Replace the RQ stuff with that. Okay, cool. So let's see. So what I'm going to do here is take both the internal data path stuff and the AW and B channels, and I need to drive those from, well, actually, AW and the B channels. Let's see, so in this case, I have two separate channels that we're operating on. So I need to drive both of these, most likely, from the same state machine here. Let's see, so in this case, I have RQ. All right, so there's a lot of stuff that needs to be set in terms of the TLP headers for PCI Express, and fortunately, AXI, we don't need to worry about, 99% of that. So in this case, we have to set all of these standard fields. Oops, that's not what I wanted to do. I wanted to select that. That's better. Okay, so the address, I'm going to keep all of these guys except for be ready. I'm just going to hold the previous value. Okay, be ready. That one gets set to 0. Okay, and then these guys go away. And I have all of these that need to be set up. So that one, these two are feedback. And these are all of the internal signals. Okay. So instead of driving stuff to the RQ interface like this and all these header fields, we drive these signals here. Oops, and this is combinatorial code, so we're going to use non-blocking, or we're going to use blocking assignments rather. Okay, and these guys I also need to take down and set these, let's see, in the stateful logic down here. Okay, so RQ T ready, take that. Okay, these all get set based on next. Oh, come on. All right. Let's do both of these in parallel here. Next, and then this one as well. I think I might have a Sublime plugin that's causing some trouble here. There we go. Okay. That looks good. That goes away. All right. So the reason I separate stuff like this is because it makes it a lot easier to write the state machines. All right, so that I will also place down here. Okay, cool. So I think that should now set most of those. We check to make sure simulation is looking okay. AXI burst size, didn't like that. Okay, 322. I think that was max. Oh, there was another parameter that I had. That's right. Okay. Let me go over here and fetch that parameter. There we go. Burst size comes from the strobe width. And max burst size comes from max burst len. All right, cool. I'm actually going to copy all 4 of those and put them right here. All right, cool. So these are a couple of other AXI related parameters. The burst size is the number of bytes that are moved in each transfer cycle. And then the burst length is the number of cycles. Let's see, and that one was specified as a parameter. Yep. And then let's see, max burst size. That's converting that back into bytes, basically. So max burst len is the number of cycles, and then max burst size is the number of bytes that can fit inside of that burst. So some of the other computations that I'm going to use, like here, instead of max payload size, I'm going to use a max burst size because I have to cut at the end of a burst. All right, so let's see here. That might run this time. There we go. That ran, and now let's take a look. I should have more of the AXI signals being driven. Okay, that looks better. WData, WLast, and WValid are not driven to anything, but that's okay. It's a start. All right, so let's see. What I need to do here is handle the data that's coming back from the RAM. So let's see here. Do is wait for a command. In this case, I'm not waiting for RQT ready. In this case, I'm going to be doing S M AXI. All right, I need to figure out what plugin is doing this because this is a problem. AXI. Oh, wait a second. RQT ready next. I'm trying to remember what that code was for. Because this one is generating that, right? Oh, right. This is yeah, okay. this is part of the pass-through. So I can actually remove everything in relation to this. I was trying to think, this is the right code. Why am I generating a T-ready signal? That doesn't make sense. Well, that was used in the previous one to pass through the read requests. So we're not doing that here. Okay, so that all of that stuff can go away. All right, so I need that. Now this is looking at the operation table to extract all of those fields. And then let's see, we're going to take a look if we have RQT ready. Okay, no, actually, again, we're not doing that anymore. So that can go away. And then we need all of this. Okay, let's see here. Op table active. EX start pointer. Okay, so this looks okay. And then I don't have anything to do with credits here, so that goes away. Sequence number enable. I think I'm not using anything in relation to that right now. I'm going to put this away for the moment. Okay, there we go. So I don't need that. Okay, so this goes ahead and does TX start, indicating that we're starting a transmit operation. All right, so let's see, I have a couple of states here. All right, so I don't need TLP header 2 because I never need to send, you know, really much of a header. TLP state header 1. Actually, can I get rid of these states completely? I think I can actually. I think what I can do here is just generate directly the AXI header. Well, actually, but what do I need to do in terms of generating the header? I need the address, I need the length, and that's it. Okay, so I should be able to generate that here, and then I just can't short circuit things like I was doing before. That's fine. All right, so what I'm going to do here, in this case, so here's how the state machine works. This one waits until the next entry in the operation table becomes active. When it does become active, then we can go ahead and start issuing, writes as stuff comes in from the RAM. So let's see this. Well, actually, okay. So this goes ahead and stores all of the fields from the operation table. So it unconditionally does that, and then once it becomes active, then it goes ahead and moves into the header state here. So for the PCI Express stuff, header 1 would generate the first cycle of the packet, which for narrower buses is the header. For wider buses will be both the header and the data. So yeah, that's where this if AXI data width is greater than 256. Because if you have more than, or if it's 128 or smaller, the header is only 128 bits, so you can generate it in one cycle, or if it's 64, you need a second cycle to generate the other half of the header. Otherwise, what we have to do is generate both the header and at least some portion of the data. So let's see. What we're going to do here is assume that we're always greater than 256 because we don't have really a header to generate in this case. Let's see. That goes away, and this goes away as well. All right. So this is now looking at, let's see, RAM read response ready. All right, so that's going to be set later on. This one is now looking to make sure that we can generate the necessary information. So let's see here. I need to generate both the header and the data. Well, those are on separate interfaces, so I guess I can probably go ahead and generate the actual write request information here. Oh, this should be done differently. That's going to be and not ready. It's AW, so it will hold that high until the transfer actually takes place. I'll do that. Okay. So what I'm going to do here is go ahead and initiate a new operation here. So this will be AXI AW valid. I'm going to go ahead and set that to high, and then I also need to have another one here. I need to be checking to see if this is ready, basically. So either need to invert this guy. It's either not valid or ready. In that case, then I can set that back to high. Okay, and then I need the two fields that are associated, the address and the length. So I'm going to go ahead and put that in here. So the address comes from, let's see, that'll be TLP ADDR. Okay, and then the length. Actually, I'm just gonna, let's see here. That should be, I think that'll be correct for now. Oh, no, that'll be cycle count. Yes. Yeah, okay, so AWLen, that's the number of cycles in the transfer. Okay, that looks pretty good for now. All right, so that, I think I might actually be able to go ahead and test that real quick. All right, so let's see, I'll get rid of that. So I don't need to generate any header now, right? I think I can just go straight on to the actual transfer. Yeah, that should be correct. Okay, so I'll go ahead and get rid of this one as well. All right, TLP state transfer. Okay, we run this. Okay, not seeing anything new here, but that's fine. Hit a refresher. Okay, hey, here's AW valid going high. And let's see, AW address is 0. That's fine. AW burst 1. AW len 0. So those look like the correct parameters there. So that will initiate a new AXI operation. The next step is to go ahead and get the actual data transfer taking place. So the TLP state pass through, that is no longer necessary. TLP state transfer. Again, all this stuff called TLP, I'm going to clean it up a little bit later. This one is to transfer the data through. So in this case, we're looking at, this is not going to be RQT ready int reg. This is going to be looking at, let's see. Where was that set anyway? Be ready int early. Yeah, okay, here we go. AXI AW ready int reg. Okay, so that one is what we need to check. If this one is set, it means that we're ready to accept a new output data word. Okay, so we go ahead and do that. Coming out of the mask rig, it update all the counters, right? We decrement cycle count, update last cycle. See, offset next, we fix that. Right, okay, and then in this case, what we're going to do is actually output the data. Okay, so RQT keep int, well, in this case, we need to look at the strobe setting. And I may need to make some more modifications as well, because for PCI Express, this is all done in terms of, let's see, this is all done in terms of D words for PCI Express, but for PCI, or sorry, for AXI, it's all done in terms of bytes. So this needs to be reworked to look at the byte enable instead. Let's see. Okay, there we go. There's our strobe connection. Data last valid. Okay, cool. All right, so in this case, what we're going to do is we're going to pass through the data, and that one is done basically the same way. Oops, there we go. All right, so that's that, and then we're going to set w valid int as well. Okay, dword count reg. I guess let's see here. So, oh, actually, I don't need to worry about tkeep. What I do need to worry about is strobe. All right. I'm gonna have to remember how to do this one. I guess I can come back and do this one a little bit later. Oh, actually, I should have the strobe computation in this DMA write module here. It's nice to have some code that I have already written that we can draw off of here. Okay, so how did the strobe computation work again? Performing the writes. Let's see. So this is generating. Okay, here's the strobe bit. Strobe input. This is coming from strobe offset mask reg. All right, so I'm gonna have to do something similar. Well, let's see if I can get just a single operation working, no matter what the strobe setting is going to be. So I'm just going to set this to all ones, and we'll see if it'll actually perform the operation. The other thing that I need as well is the TLast signal, or not TLast in this case, because we're talking about AXI. I'll comment that out. Okay, so we got wdata, right? We got wstrb, which is a to-do. Right? And then we have wlast. Let's see. So last cycle reg here. If it's the last cycle, then what we need to do is finish the operation. So in this case, what we're going to do is set wlast high, indicate that it's the end of the operation. Okay, cool. And then we also need to mark that as finished. And I will deal with the skipping idle states later. So we can just go straight back to idle at this point. That's a useful optimization that saves a few clock cycles here and there. Okay. Uh-oh. Let's see, 830, I have a syntax error. Oh, all right, let me just delete this. I put that in there for reference. I don't need it. Okay. And there we go. Okay, so that performed write word ID 0 into the RAM. So we read 11223344 from the segmented interface, and we wrote 11223344 to the other interface. So if we hit refresh there, that looks pretty good. There's the data going out, and then I need to process the B channel. That will be a problem for another day probably. Let's see. So we have wvalid going high. That's interesting. Oh, I need to take a look at that actually. Wvalid. Okay, wready is high, wvalid is high. Why did it leave that? Oh, probably because it didn't leave that state. Is that what happened? Maybe. Anyway, so wlast is high, wvalid is high. That looks pretty good. Let's see, and this is, why is it showing all X's? Oh, because I need to initialize these here. Okay. Cool. So I'm going to go ahead and comment those out. Wvalid set to 0. Wlast. I'll just set all these to 0. And do something more intelligent later. All right. There we go. That should issue a single write operation. There we go. There we go. So we have wdata. If I zoom in here, well, I can just show you here. There we go. 11223344. So there we go. We read that from the segmented interfaces, and we issued a write operation over the AXI interface. So the next step is I have a lot of cleanup to do, and I need to go through and properly implement a lot of these rules. The nice thing about writing to address 0 is you don't need to worry about any of the shifting and making sure that's correct. I have a suspicion that the test bench for this is going to take quite a while to run to test all the possible offsets, but I'll go ahead and get that all dialed in a little bit later. Let me actually do one more thing really quick. I'm going to go ahead and add, let's see, this is the AXI DMA IF. I'm going to go ahead and I'm going to comment out, I think it was blowing up on this assert statement. What I can do is perform a read against the internal RAM here. So this is going to be, what was it? AXI RAM inst read mem AXI address. I'm going to read 32 bytes. Okay, and then I can also do the same thing, and I can assert that this guy equals the test data. Okay, let's see, what was this? This was what's the length? Oh, len test data, right? Okay, cool. Let's see if that works. So there we go. It passed. It did write the data out to the location where it needed to go. So yeah, there we go. Read the data from one interface and wrote it to the other interface. Obviously, we need to do a little bit of cleanup, but it worked. All right. So does anybody have any questions or anything else you want to see? Otherwise, I'm probably going to sign off for the moment. No? All right. Fair enough. Well, thanks to everybody who stayed for the whole stream, and happy hacking.